Okay, ready?
Yes.
Okay, welcome everyone. This is the second lecture in our Young Scientist series, and this afternoon we have Tana Joseph from the University of Cape Town. Tana decided already to become an astronomer at the age of 11, she tells us, after seeing images of astronomical objects taken with the Hubble Space Telescope. She completed her PhD at the University of Southampton in 2013, and she also spent time in the Harvard-Smithsonian Center for Astrophysics. Today, she is a postdoctoral research fellow working on multi-wavelength studies of high-energy binary systems, and she will, of course, explain what all that is about. It's Greek to me.
Good afternoon, everyone. Can everyone hear me? I'm not sure if the mic is on. No. Okay. Now? Yes? At the back? Okay. Good afternoon, everyone. My name is Tana Joseph, and as I've been introduced, I am a postdoctoral fellow here in the Astronomy Department, so right at the other end of University Avenue in R.W. James building. And as you can see from the little badge, so that's the UCT badge, to show my UCT affiliation. And then I'm actually funded by the SKA South Africa project, which I will be talking about more as we go through this talk. So today I'm going to be talking to you about multi-wavelength astronomy in Southern Africa. It's all very new and exciting in Southern Africa because we are becoming a hub for astronomy in the world. And the reason it's Southern Africa, not South Africa, is because one of the instruments I'm going to be talking about is actually in Namibia, not in South Africa. And I will explain as we go through what I mean by multi-wavelength. So just to give you sort of a brief background of astronomy, I like doing lots of public outreach talks for astronomy because I always feel that it's so accessible to just about everyone. Most human beings have looked up in the sky at some point and wondered what it is that they're seeing. Why are some of the dots that you see white? Why are some of them blue? Why are some of them red? Why aren't there any green ones? Why do some of them move faster than others? These are all questions we've had before while looking at the night sky, and they are science questions because they're the physical reasons why some stars are bluish and some stars are reddish. And throughout human history, we've looked to the sky to try and make sense of what we see, to come up with stories to explain the night sky. For example, the Khoisan peoples, the Mayans are very famous. The ancient Chinese are very famous also for keeping very good astronomical records of developments in the sky. And so I think this is sort of a basic thing that all people who look to the sky experience. So it's something that connects all of us. And one of the first people to make a huge breakthrough in actual sort of more modern astronomy is Galileo Galilei. And in the very early 1600s, he was one of the first people to develop a telescope. And he was actually the first person to see 4 of Jupiter's moons, the 4 biggest moons, and also the rings of Saturn, which are now very well known and quite famous. And what I always say is these optical telescopes, so you basically just took some lenses and put them in this sort of long tube, and he looked at the sky. So it's just kind of an extension of what your eye would see. The size of those lenses is about 10 centimeters. So if your eye the pupil of your eye was 10 centimeters big rather than just about 1 centimeter big, you would also be able to see Jupiter's moons and the rings of Saturn with your naked eye. So basically the difference between our eyes and this telescope of Galileo's, so that 10 centimeter aperture there is that is 10 times bigger than your eye, and that's the only difference. The same kind of light goes in, the same kind of process happens. It's just that he basically made his eye 10 centimeters big by looking through the bottom of this telescope. And so with the optical telescopes just being an extension of our eye, because they allow your eye just to be slightly bigger, you basically only see this really narrow range in what we call the visible, because it's what's visible to our eye, and covered by this rainbow spectrum that we're all familiar with. But there are lots of other types of electromagnetic radiation or electromagnetic emission, what you can kind of class all as different kinds of light. The low energy side, we have radio waves, microwaves, and infrared, and they're all lower energy than the visible. And then higher energy, or what we also call ionizing radiation, so it can be quite harmful to us as living beings, is ultraviolet, which we're all familiar with. That's the stuff that gives us sunburn, so we know it's dangerous. X-rays that we use to, for instance, in a terrestrial sense, to image broken bones and so on. So we know that in order for that X-ray to actually make images of our bones, it has to go through through our skin, through our muscles, right to our bones. So we know that that X-rays are very high energy because they pass right through you, and they can actually cause damage as they pass through you. And then gamma rays, which you might know, in popular culture, they like to blame gamma rays for creating mutant monsters or superheroes and things like that. And they're the highest energy electromagnetic light, electromagnetic radiation that we have. And so if you want to know more about the universe, you need to kind of explore all of these other windows, all these other types of radiation. And here's just, so this little squiggly line here shows you sort of the size of the waves for the various types of radiation. So the longer waves are the lower energy, and they also correspond to the lowest temperatures. And then the higher the energy, the shorter the wavelength, the higher the temperature. So the temperature one is sort of something to bear in mind, because we all know the hotter something is, the more energetic it is. So if you kind of think about it as a temperature, so things that emit gamma rays and X-rays are going to be the hottest or the most extreme types of systems. And the cooler it is, the less extreme it is, and then you move into the longer wavelength regime. So we started with optical observing in the very early 1600s with Galileo Galilei, but there are lots of, as we just explored, just seen, there's lots of different light to explore, and so a different way to look at the universe is to try and actually image these other light waves that are coming out at different frequencies or due to different temperatures. Carl Jansky was the pioneer of radio astronomy, and this is his radio telescope that he used. In 1931, he detected radio waves coming from the center of our galaxy. And he worked at Bell Labs. And this was actually a communications telescope. Think of it a bit like a DSTV dish, like used for our purposes. Here it was used for telecommunications. And then he repurposed it and pointed it at the sky and put a different type of receiver on, a much more sensitive receiver, because the emission coming from the universe is much fainter than terrestrial sources. So he put a more sensitive receiver on, and then he picked up radio waves coming from the center of our galaxy, which was a first. So Carl Jansky is the pioneer of radio astronomy. And now today we have the VLA, the Very Large Array. How many of you have ever seen that movie Contact with Jodie Foster? Yeah. So the white telescope that she's listening to, it's the VLA. So this telescope is a movie star, featuring Oscar. It starred along Oscar winner Jodie Foster and held its own, I think. Did a very good job in that movie. And the VLA was recently upgraded and renamed in honor of Charles Jansky, so it is now the Jansky Very Large Array, and it is currently the most powerful radio telescope in the world, and it consists of about 27 dishes. And these dishes, if you can just see here, they're on tracks. So this is what we call the most photogenic pose. This is the D array of the most compact array configuration for the VLA, and you can move it along the tracks and extend out, and they extend out tens of kilometers in the New Mexico desert. And so then, depending on the distances between these dishes, you can image different physical scales of the object that you're looking at. But for photo purposes, they like to put this in what we call D array, because you can fit all the dishes in really nicely.
Are those things listening?
They're not listening. They are they are catching radio. Radio is a misnomer, so not radio like the sound waves that you hear coming out of your radio, but radio waves, which is actually what carries the sound from the antennas, from the transmitters to your radio, and your little antenna in your radio picks up the radio waves and converts it to a sound wave. So radio waves in this context are not sound waves. They are electromagnetic radiation. So exactly how you think of light, like it travels through a vacuum and that kind of thing, not like sound waves, which wouldn't travel through a vacuum because you actually need physical material between you and the thing that's making your sound to be able to hear the sound that's being emitted. That's why often in things like Star Trek and so on, they have explosions. You can hear the explosion in space. That's not physically accurate. Because sound waves don't travel in a vacuum, and space is mostly a vacuum. But light waves do, and radio waves are just a type of light, a low energy type of light. So in the 30s, that was the advent of radio astronomy. Then in the late 40s, we decided to open up another new window in the electromagnetic spectrum and start looking at high energy emission from X-rays. And I think a lot of this was prompted by military reasons, because people wanted to keep tabs on what nuclear powers were up to and whether they were doing nuclear tests. So things, because these nuclear tests give off things like gamma rays and high energy X-rays, so astronomy kind of just jumped on the bandwagon and said, oh, let's use these military things and see if we can see something in space. So initially, when they launched these rockets, they were trying to detect, to keep tabs on nuclear tests, whichever countries were involved in this. But then actually, they were repurposed for astronomical purposes, and the first X-rays were detected coming from our sun, our nearest star. And this was just a rocket that was launched, so it went up just outside Earth's atmosphere and came back down. It was not a permanent satellite. The first permanent X-ray astronomy observatory was launched in 1970, and that actually did orbit the Earth for some length of time, and it was called Uhuru. And since 1970, over a dozen X-ray satellites have been launched into orbit. And then going to the highest energies, in 1960, Explorer 11 was the first gamma ray detector launched, and it detected less than 100 gamma rays. And since then, more than 10 gamma ray telescopes have been launched. So this is a very interesting one. So there are also ground-based gamma ray telescopes, and that is the reason you can do ground-based gamma ray detections and not ground-based X-ray detections is because gamma rays are they're much more energetic than X-rays, and the way they interact with the atmosphere, the Earth's atmosphere, allows you to be able to detect the aftermath right here on the ground. And I will explain more about that later, but this is the telescope that is in Namibia. So now I've talked all about these different kinds of light and the high energies and the low energies, and you're probably wondering, but why do we care? What difference does it make whether you look at it with radio or with infrared or with UV? So I'm going to just go through some examples and show you what happens when you image the sky or image various astronomical objects using different types of light. So this is the Crab Nebula, and this is what we call a supernova remnant, and it was what was left behind when a giant or massive star, at least 20 or 30 times the mass of our sun, exploded. And this Crab Nebula is very famous. It's been studied for a long time, and it was actually first seen by Chinese astronomers in 1054 AD, and it was bright enough to be seen with the naked eye during the day. So one day they looked up at the sky and they just saw, oh, there's this really bright new star, and they kept track of it in their records and watched it fade with time over weeks and months. And so what we see here is, this just looks like a cloud, and that's actually what nebula means. This is a cloud of dust that was flung out when this huge star exploded when it died. And you get these different colors here. And this is an image taken with the Hubble Space Telescope. And this is what your eye would see if your eye was 10 meters big and in space. Oh, no, sorry, not 10 meters, 2 meters. 2 meters big and in space, so outside the Earth's atmosphere. And so these are all optical colors. This is the kind of light that our eyes can already see. And you see all the different colors, and the blue and the green are oxygen. The orangey color is hydrogen, and the reddish color here is nitrogen, and the yellowy color is sulfur. So these were all chemicals that were manufactured by the star as it fused heavier and heavier elements together, and then when it ran out of fuel, it exploded. So this is really fantastic, because just from this one image, we can test, for instance, our theories of stellar evolution, because the way we think stars work and how nuclear fusion works inside stars, heavier and heavier elements will be formed, starting just from hydrogen, and then you build up heavier and heavier elements as the fusion processes continue. And from this one image, we can see that that is actually what happens, and they come out in nice layers. They come out in nice layers with the lighter things towards the edges and getting heavier as you go in. And that's exactly what the theory tells us. But now the problem is that the theory also tells us that who knows what you're supposed to get when a star explodes? What's supposed to be left behind? Black hole or a neutron star. But this amazing Hubble image doesn't show you that. So that part of our theory is not supported by this evidence. But that's why you look in the X-rays, because black holes and neutron stars are very high energy, very extreme objects. And so you would expect the light coming from them will be caused by these extreme physical interactions and this extreme physical environment, so they would be higher energy photons coming out. And this is a Chandra Space Telescope image, an X-ray image, and right there you can see the neutron star. This is the same source. This whole purple thing fits in roughly in the area where the bluish light is. And so out pops the neutron star, just like we expected. There's a jet of radiation coming out, which is also what we expect from the theory. The neutron star spinning very fast. And you can see from this X-ray gas, this halo of X-ray gas, you can see that it looks like it's spinning like a top. So just from this image, you can verify there's the neutron star, there's the jet of material that we expect, and it's spinning really fast. Boom, done. But you wouldn't be able to see that just from here. This is why in order to get a more complete understanding of astrophysical objects, we need to look in the various different windows in the electromagnetic spectrum.
So is that the same object?
That is the same object. This is the cloud of gas and dust that was thrown out when the star exploded, and this is what happened to the main core of the star. So it collapsed from something that was about 30 times the size of our sun down to something the size of Cape Town. That neutron star weighs about the same as our sun, but it weighs the same as our sun, but it's the size of a city. It's about 10 kilometers, 20 kilometers across. So extreme physical processes, something huge being smushed into something really small.
Where is the right image in the left picture?
So this purple fits roughly in where the blue is.
All of the blue?
Yeah. So this central size here, that fits in roughly about there.
Is the energy proportional to the square of the frequency?
The energy emitted?
Yes.
The energy of the...
Of the radiation?
Not the square of the frequency. It goes linearly. Energy scales linearly with the frequency of the emission. Yeah. So without the X-rays, you wouldn't be able to see this very important astrophysical object that we think from theory should remain after supernova explosion. So I'll give you another example. This is a galaxy called Centaurus A. It is very near to our galaxy. For such a massive galaxy, it's about 15 million light years away, and it was first discovered in the 1800s. So we've known about it for a long time. And this is an optical image taken of this galaxy, and you can see most of this kind of bright diffuse light here is from the stars in this galaxy, and it's a roughly sort of a rugby ball oval kind of shape, and it has this pretty dust band going through it. So it's not a spiral galaxy like our galaxy. It's more what we call an lenticular or an elliptical, because it doesn't have spiral structure, but it has this interesting kind of structure here of dark material that's gas and dust, and that indicates that perhaps this galaxy has it's a result of a merger. So two galaxies that flew into each other and coalesced to form this kind of pretty halo of light type galaxy. And that's what your eye would see again if you were in space and your eye was a few meters big. But this, again, is the same galaxy. So this optical image has been overlaid with the purple is radio, and this white jet coming out of here and the white light here is X-ray. So this is the same galaxy. So this looks like a super boring kind of galaxy, very smooth, and only this little bit of like this ribbon of darkness. But actually, if you look in the radio, you see these huge lobes, these huge emissions of radio waves. And these radio lobes, this radio kind of jet that bends down like that, that is 1 million light years long. And there's no indication of that here, none. This X-ray jet coming out of here is also tens of thousands of light years long. And there's absolutely this thing looks super quiet and boring, but there's all this going on. And you can actually even see now the resolved better the dust lanes. And so the radio jets and the X-ray jets are coming from a supermassive black hole that weighs about 50 million times as much as our sun. So it's about at least 10 times bigger than the supermassive black hole in the center of our galaxy. And because our galaxy doesn't, the black hole in the center of our galaxy is not big enough to eject these huge sprays of radiation. So immediately from this image, you can see there must be a supermassive black hole powering these jets, and that tells you about the structure of the galaxy. And also, it's very, these jets are very far-reaching, and they have lots of influence on things like enriching what we call the intergalactic medium, with injecting it with energy, starting up star formation processes in galaxies, and so on, and just kind of recycling energy back into the interstellar medium and the intergalactic medium. And without the X-ray and the radio, you would never be able to pick that up. And one thing as well about what we know from physics tells us that when you have strong outpourings of radio emission like this, that is usually caused by magnetic fields. So we have insight into not just that there's a supermassive black hole at the center of this galaxy, but also that this galaxy has very strong magnetic fields. And magnetic fields are, I'll let you in on a little astronomy secret, but you must promise not to tell anyone. When we don't know in astronomy what's going on, we'll say it's probably magnetic fields. We don't know the exact specific mechanism that launches jets. We know that they exist. We know that jets are launched, often from black holes of various sizes, but we don't know the exact mechanism because black holes don't have a surface. So the magnetic fields can't be anchored to anything, so it's kind of complicated. But the thing about magnetic fields is that they're very difficult to model. It's very computationally intensive and mathematically difficult to work through the calculations involving magnetic fields and then model that on a computer is very time-consuming. It's only sort of in the last 10 years or so that we've had the computational power to be able to start unpacking magnetic fields in astrophysical scenarios. So I'm going to say magnetic fields. We'll just move on now. You guys are in the know. But the physics is sound. We know that when you have large-scale strong magnetic fields, it should give rise to large-scale strong radio emission. But we're not 100% sure, for instance, of this jet launching mechanism yet, but magnetic fields. And here's another example. This is G327, and it's also a supernova remnant in our galaxy, just like the Crab Nebula. And as you can see here, this is obviously an image of a star exploding. That's definitely what that is. This is an infrared image, and from this infrared image, we can definitely see that, right? Everyone can see the exploded star. It's perfect. I don't even need to explain. You guys know all about that now, because it's very clear in this image. But of course, all we're seeing is background stars. We're just seeing infrared emission coming from background stars. But if you look in radio and in gamma ray, and there's even some X-ray in this image, all of a sudden you can see it. this is the fast-spinning neutron star that's left, and it's giving off a lot of gamma rays, because the white is gamma rays. And then it's surrounded by a halo of gamma ray gas, gamma ray emitting gas. And then the red is radio emission. And it's nice and concentric. It's much more spherical or circular than the Crab Nebula, and that's also kind of more what you expect, because a star is a spherical object, so you expect it to kind of explode all in the same direction. And that's exactly what this has done. And so this is in infrared. The source doesn't emit very much at all. But there is brightest day, the neutron star in the gamma rays, and then there's this halo of radio emitting gas, and that tells you that there's strong magnetic fields in the gas surrounding this explosion.
What is the PSR?
PSR is short for pulsar. So pulsar is just a rapidly rotating neutron star that emits pulses of pulsed light. So this is why multi-wavelength observations are so important, because think of all the things we were missing out on, all the things that we overlooked or couldn't explain because we didn't have enough information. And now you can put all the pieces together. You can know about the magnetic field strength. You know about what we call the compact object, the neutron star, or the black hole that remains, or the black hole that's powering various structures like jets that are millions of light years across, and so on. And so this source is not emitting much X-rays, but the little green dots you can see there, because that's X-ray emission, that's probably from neutron stars in the background, or black holes in the background behind the source. So there we've picked up some neutron stars, and you can go and study those if you want, which is part of my research. So now on to the instrumentation that we use to collect all of this multi-wavelength data. And the first one I'm going to talk about is the Southern African Large Telescope, or SALT. At the moment, it is the crown jewel of South African astronomy. It is the largest optical telescope in the Southern Hemisphere. And the mirror inside there is 10 meters big. It's made up of lots of small mirrors, but together the collecting area is that of a 10-meter mirror. And it exists just outside Sutherland in the Karoo. So this is a schematic diagram of inside the dome. So that mirror there is 10 meters big. And that's the rest of the dome. There's the optical camera and the instrumentation that we use to collect the light once it's reflected off the mirror and so on. And down here is where you sit with a computer looking at the images that's been taken by this telescope. So yeah, this telescope was completed in 2005, and which is when I graduated with my BSc, my first degree. So when I was 11 years old and I decided I wanted to be an astronomer, people thought I was a bit weird, but they indulged me because I was quite a cute child. So they were like, "Oh, that's adorable," I guess. And they thought I would grow out of it. And when I got to high school, I still hadn't grown out of it. And people used to say things like, "Oh, but where are you going to work? We don't do that in South Africa. You have to go to America. You have to go work at NASA. How are you going to do that?" So a lot of awkward questions like that. But my parents were steadfast, and they knew that something like being like a medical doctor is probably not the best thing for me because I'm very clumsy. Life should not be at stake in any job that I do, is what I'm saying. And then they announced that they were building SALT, and then kind of overnight the questions went from, "Oh, but how are you going to be an astronomer in South Africa?" to, "Oh, are you going to work at SALT?" And so it was fantastic timing that by the time I finished my BSc in physics here at UCT, this fantastic instrument had been completed, and the government had also started various programs to train up astronomers and other support staff such as engineers and so on to do science and also maintain and build this telescope. So this was a huge game changer in South African astronomy. And so that was the optical. Now we're going to go to the radio and the instrumentation that we use to collect radio data here in Southern Africa. Who of you guys know about the SKA project? The SKA South Africa project. So you're all familiar with the enormous radio telescope that we're building out in the Karoo. And when it's done, it's going to be the premier radio telescope in the whole world. So the VLA has to take has to take a bow and be second best. So before we build the SKA, we're building this instrument called MeerKAT. And before we started building MeerKAT, we first built a test instrument also called KAT-7. So KAT stands for Centaurus A telescope, and 7 because it consists of 7 dishes. And this was completed a few years ago, and we've been using it to train students and to learn how to do radio astronomy. Because this is the first radio interferometer, and I'll explain in a second what interferometer means, in South Africa, where countries like Australia, who are jointly hosting the SKA, so there's SKA Australia as well, they have radio interferometer experience going back decades, and we don't, so we were playing catch-up. But this is a fantastic, nifty little instrument, and it's doing fantastic science. So this was the precursor to MeerKAT, which is the precursor to the SKA. And when it's done, it will consist of 64 dishes. I was there in early December last year, and 12 of the dishes were up. So it's moving along at a great pace, and we hope to have completed all 64 dishes by the end of this year. So I'll just give you some background on why it's called MeerKAT. So initially, this telescope, the 64-dish telescope, was only going to consist of 20 dishes, and it was going to be called the Centaurus A telescope, because it's in the Karoo, and it's an array of dishes that we connect together electronically to form this big radio telescope. But then, to boost our bid, because we were up against experienced countries like Chile. Chile has some of the best astronomical instrumentation in the world. We're up against Australia with decades of experience of radio interferometry. The government stepped in, and they gave us more funding to build more telescopes out to make our instrument better. So it went from 20 dishes to 64 dishes, and that's where the Meer comes from. So it just literally means more cat. And also the little cute animals that everyone knows are also indigenous to this area of the Karoo. So you see them. I didn't get to see any of them. I did see a scorpion though, so that wasn't as exciting. When I went and visited the KAT-7 site, and then not far from that is where they're building all the MeerKAT antennas.
Where is that?
That's in the Karoo, near Carnarvon. Yeah. So on to the big show, the main event. So once MeerKAT is complete with the 64 dishes, it will be the largest radio telescope in the southern hemisphere until SKA is complete in about 10 years from now or so. And SKA will be spread across across Africa and Australia, because you can see from this image the yellow dot is the main area now near Carnarvon where they're building, and then they're going to be sort of clusters of little groups of telescopes, because each dish is about 13 meters across. And it'll spread across South Africa. They'll be in our neighboring countries, in Zambia, and in Ghana, and in Kenya, Madagascar, and Mauritius. So it's a pan-African endeavor, and we are already training up students from all over from these countries in Africa. They're studying here at UCT and at the SKA office in Pinelands, and at Hartebeesthoek and so on in Joburg, so that once their dishes are complete, they can take the reins and use these instruments for science in conjunction with all these other satellites or these other dishes. And it's a very exciting endeavor, especially for me personally, because my science, so I work on X-ray binaries, and I can talk more about that at the end when we do questions and so on, basically requires all of these dishes to work as one big telescope. It's very ambitious, but people seem to be, again, they're indulging me, they're not saying no. So I'm going to ride that. So I always talk about how we're definitely going to go, once this is spread across Africa, it will be called the African Very Long Baseline Interferometry Network. And it will be very sensitive, and we'll be able to probe very, very small scales of whatever kind of astrophysical object you're looking at, whether it's galaxies or binary stars. And you'll be able to see the very fine detail and get down, probe some really interesting physics. But all of this has to come online, and all of this has to work now. So I'll be nearly 50 by the time that happens. So I'm starting to lure students in now into my research, and hopefully by the time they finish their PhDs and have some research experience, this instrument will be online, and we'll be ready to do our science. So I keep using this word interferometer. And I said I'll talk about it, and now we're going to get down to some technical stuff, so hopefully there's some engineering people here, maybe can lend a hand. But basically, what a radio interferometer is, it's just a collection of radio antennas connected via electronics. So they're not physically connected. So it's as if you took, so the square kilometer array is basically as if you took one giant dish that has the surface area of one square kilometer, but instead of making one giant dish, you can imagine that it'll be very difficult to maneuver. You won't be able to steer it without it deforming, and it's just not feasible from a structural point of view. So you break up that square kilometer into lots of little dishes, the 13-meter dishes, but you connect them via electronics. And so the way they move and what they detect, it's as if they are one dish but spread over a much larger area. And so inversely, to sort of counterintuitively, the further apart the dishes are, the smaller physical probes that you can resolve. So we all understand what I mean by resolution. So the fine details that you can see, for instance, SALT. I think SALT's resolution is such that if you put a 2-rand coin and a 5-rand coin on the moon, you should be able to see the difference between the 2-rand coin and the 5-rand coin. So you won't just see 2 silver blobs. You'll actually be able to see 2 rand and 5 rand written on it. So that's what I mean by resolution. You'll be able to see details. So with a radio interferometer, you can imagine if we're spreading it across continents, across the continent of Africa and across Australia, the resolution that we'll be able to obtain versus the VLA, which only has distances of tens of kilometers between its antenna. So it's just a completely different ball game now with the SKA. So this is what it is. And so for instance, these 3 antennas are pointing at something, some black hole, and they're all at various points on the ground. But the radio emission, the light will hit this one first, then it'll hit that one, then it'll hit that one. But in order to make a coherent image, you then have to delay so this is where the electronics comes in. They all fed into this, all the emission, the detections data is fed into a correlator, and the correlator knows very precisely the position of each antenna, and then it will delay the signal coming in from here, and then slightly less of a delay on the signal coming in from here, so that all the signals come in at the same time. And so that's how you build up a coherent image with different antennas. And so a lot of the thing about radio astronomy is the expense is not so much in the hardware, and it is in the software, in the signal processing and all that. You can imagine with 3,000 antennas, which is what the SKA will be when it's done, it's going to be an enormous undertaking to have the computing power to be able to keep track of all of these things, especially spread across continents, because the radio interferometers are so sensitive that the VLA routinely can measure plate tectonic movement. That's how precisely we have to know where each antenna is. So the movements, and they say plate tectonics, the movement of the plates on the Earth's surface is roughly the same rate at which your nails grow. And that radio detector picks that up like, oh yeah, no, it moved 2 centimeters over here, and we need to account for that. So that's the kind of detail, the kind of high spec electronics that you need to make a radio interferometer work. So it's a huge undertaking. And now I'm going to also talk about the radio observatory in Hartebeesthoek, which is about 50 kilometers from Joburg. And it was built in the 60s actually by NASA as a communications satellite in order to keep track of their unmanned space probes. And then in the mid-70s, this dish was handed over to us and repurposed as an astronomical observatory, and they do things like measure the spin rates of neutron stars and how the spin rates change, because neutron stars are spinning neutron stars or pulsars are the most accurate clocks in the universe, and we can detect changes in their spin rates because they're so constant down to like the 15th decimal place. And that's the kind of work you can do with Hartebeesthoek and other similar radio telescopes. And Hartebeesthoek, once is often linked up to the VBLI, so very long baseline interferometry. So the baseline is the distance between the antennas, and interferometry, as we just discussed, is joining them up. So you can join up things in Australia, in Joburg, in America, all over the world. And so you can imagine the kind of resolution that you get when you go global. And there's also this little space one here. And so radio interferometry is the way forward. And once we start filling in the gaps here with the African VLBI network, it's like, once again, it'll be a huge game changer and a very exciting time to be in astronomy. So this is the Hartebeesthoek 26-meter dish, and you can actually walk in there. Sometimes as a student, they'll let you go and like walk inside there. And so I said that KAT-7 was the precursor to MeerKAT, and MeerKAT is the precursor to the SKA. And the precursor to KAT-7 is this 15-meter dish that they first built at Hartebeesthoek. So this was the practice for MeerKAT, for KAT-7, and then they expanded KAT-7 to 7 dishes, and then we're going to have MeerKAT, and then we're going to have the SKA because, there was a lot of catching up to do, and we're doing very, very well. The Australians are a little bit nervous. And now I'll come to the last instrument, which is the high-energy Spectroscopic system, or HESS, which is a ground-based gamma ray observatory located in Namibia. And this instrument consists of 4 12-meter dishes. These are just mirrors. These are optical telescopes, and one 28-meter dish in the middle. And it's also used as an array of smaller dishes to make up kind of one bigger collecting area. So this instrument is an imaging Cherenkov radiation detector, and we will unpack what that means. So normally high energy, the purpose of the reason that we manage to exist here on Earth and not get bombarded all the time by space blasts of high energy radiation like gamma rays and X-rays is because our atmosphere protects us, and it's about 10 meters thick, and these blasts of high energy radiation come in and they basically get absorbed by the atmosphere, so it doesn't harm us, except for that pesky hole that we made in the ozone layer that allows UV rays through. So we mustn't do that, it's bad times. So what happens with the X-ray, for instance, which is less energetic than a gamma ray, what you'll get is the X-ray will come in and it'll be absorbed at the top parts of the atmosphere before it can come down and do damage to us. But gamma rays are much more energetic. So what they actually do is they interact with the upper atmosphere in such a way that the molecules here, they interact almost like CERN, like a particle collider. So this gamma ray comes in and it smashes through things and it deposits its energy in these molecules, and it actually makes more particles come out, like muons and things like that, and then that's like a knock-on chain reaction, and you end up with this thing called a particle shower. So one particle or one photon comes in, very high energy gamma ray photon, and then it causes this particle shower to occur. And this particle shower emits this blue light called Cherenkov radiation, which is named after its discoverer. And how this blue light arises is this gamma ray is so energetic and it imparts so much energy into the molecules at the top of the atmosphere that in this particle shower, some of these particles are actually moving faster than the speed of light in the atmosphere, not faster than the speed of light in a vacuum, because as we all know, that's the fastest, that's the speed limit for anything in this universe. But light moves slightly slower when it's moving through gas, or it's moving through water, or stuff like that, or moving through some kind of material, and not in a vacuum. But these particles have got so much energy from these gamma rays smacking into them that they actually, not by very much, but they actually exceed the speed of light in what the speed of light is in the atmosphere. And that physical process causes the particles to emit this blue Cherenkov light in a very specific shape, because this is a very specific physical process that you only get with photons that are sufficiently high energy and in specific densities of a medium that it's moving through. So it's very specific physical conditions, and what you get is very specific type of light at a very specific frequency, in this case the blue, and in a very specific shape. So it's very tightly constrained. So this blue light is very tightly constrained. And this blue light is what is detected by the ground-based gamma ray telescope. So you're indirectly measuring gamma rays. But because you know that because you know the frequency of the light very, very well, it's tightly constrained, you know the shape of the Cherenkov cone very, very well, you can work backwards and figure out where that gamma ray actually came from and at what energy. And so that is how you use ground-based gamma ray telescopes to indirectly build up an image of gamma rays emitted from various astrophysical sources, like that pulsar that we saw earlier. And so that's quite a nifty trick of exploiting the known physics to be able to do much cheaper astronomy, because as you can imagine, it's much cheaper to build four ground-based telescopes than to launch something dedicated into space. And we wouldn't be able to do that because we don't have that kind of space program in Africa. But HESS in Namibia is the leading, by far, the leading ground-based gamma ray telescope in the world. So just to conclude, I'll show you some images. So we saw, this is Centaurus A again, the suspiciously quiet-looking in optical galaxy, but actually has all that X-rays and radio jets coming out of it. And if you use HESS, you get this tight little knot of gamma rays coming from just outside the black hole. And you can see a slight extension there, and that's probably in the direction of the X-ray jet. So the X-ray jet has there's also some gamma ray emission coming out in a jet-like structure. And this is all very high energy photons coming from just outside the black hole. So that just shows you that this black hole is a very, very extreme object. And then this is a KAT-7 image of Centaurus A again. And these are the radio lobes. So those big purple, nicely defined radio lobes that we saw, but that was taken with a VLA, remember, with 27 dishes and tens of kilometers between the baselines, whereas KAT-7 only has 7 dishes, and the longest baseline is 185 meters. So you can still definitely see, even if you didn't have a VLA, you would be able to look at this image and say, oh, there are these radio lobes coming out of this galaxy, and it has some gamma rays coming from the huge compact object at the center, and you can measure the size of these lobes and the energy coming from it and magnetic field strength and so on. But you don't get the fine detail because you don't have the huge distances between the antennas the way you do with a VLA. So this is the kind of science that you can get with HESS, with KAT-7. Unfortunately, I couldn't source any particularly nice images with SALT, but I assure you that it's working fantastically well. SALT was in the news in last week because there's a new exciting and very strange supernova that went off, and we don't understand it. And SALT was one of the array of telescopes used to follow up on this and to learn more about the source. So watch the news for SALT news, because this supernova is baffling us. We don't know. And I don't think it can be explained by magnetic fields. Okay, that's the end of that. So we have 10 minutes for questions. Yes? That is a very good question. And as taxpayers, you should ask that question because your money is paying for this stuff. So I'm always happy to answer that question. So one of the things is, so the question is, what benefit is astronomy or all this kind of stuff to the general public, to people who aren't scientists? Because I'm standing here super excited about this, but I mean, you know, that's me, that's what I chose to do for a living. So there's I'll answer that in 2 parts. So very specifically to South Africa, the government has designated the SKA project, for instance, as a key science project for this country. So it's used as a driver to grow science and things like engineering in this country, which we all know, sadly, we're lacking, especially things like engineers. We need a lot of more qualified engineers. And not everyone that starts doing a BSc in astronomy or physics will end up being an astronomer. So what we're hoping is that this is the kind of thing that will kickstart people being interested in doing physics and science, and especially maths at school. And what what that can lead to is, what you get during your education is a lot of transferable skills. So a lot of people go into finance, they go into tech startups, and so on. So when I was doing my PhD at the University of Southampton, I started in 2009, and at that point, that was just after the financial crash. And so one of the first budgets to be cut is blue sky science, like astronomy. And so there was one postdoctoral position available for every 6 graduates at that stage. But it's not, but we are the least, we have some of the lowest levels of unemployment because we are so sought after in various other professions like finance, like banking, even teaching, and so on. So basically this is, we're going to use it as a driver to get people interested in science, to get people doing subjects that are sought after, and so that they can go into professions that are lacking, such as, well, engineering is one. There aren't enough engineers in this country, and you can go to university on an SKA bursary, and then after that 4 years decide you don't want to work on the SKA, you want to go and use your electrical engineering to help to work on research for sort of renewable energies and so on, and that will benefit the country. So that kind of expansion of getting more graduates through is one thing. And then the second way to kind of think of it for blue sky science, just in general, there's like CERN is another classic example of what's the point of smashing small things together? What do we get out of it? We all know what the Higgs boson is, but how do I control the Higgs boson so that I weigh less on my scale? We're not there yet, but one day. So the classic example coming from CERN, for instance, is the World Wide Web was invented by Sir Tim Berners-Lee at CERN, completely unrelated to particle science. He just wanted to make a way for his computer to be connected to his colleagues' computers so that they can transfer files and communicate more easily with each other, and then he accidentally created the World Wide Web. So another example is CCDs, the charge couple devices that they use instead of using huge photographic plates. The astronomers started using these CCDs, so electronic detectors on the telescopes, and that's why we can take selfies now, because no one uses film anymore. So once CCDs were used for astronomy, they became more used and they became more commercially viable. And basically, inside your camera phone, inside the camera on your phone, is a little CCD that was first used in astronomy and first pioneered there. And so every time you take a selfie or you see a selfie, you're like, that's because of astronomy. And we all know how super popular selfies are. So just the kind of unexpected bonus that you get out of blue sky science literally changes the way society works, because where would we be without the World Wide Web? And where would we be without selfies? Yes?
Work with Bernie Fanaroff at all?
The question is, did I work with Bernie Fanaroff? So, no, I didn't, because so he's just retired as the director of the SKA, or the head of the SKA project. But I think he retired from astronomy in the 80s, and then he went into business.
Yeah, but he was actually sort of headhunted again.
Yes, yes, and he did a fantastic job. So they drafted him, they got him out of not doing astronomy back into astronomy, and he spearheaded the obviously successful SKA bid. And so I didn't work directly with him, but he does know me. He always comes to our bursary conferences that students give and their postdoctoral fellows give, so he does know me. And I was actually funded by the SKA for my MSc as well. So I was one of the first bursars, the first recipients of an SKA bursary. So they've known me basically throughout my astronomy career.
And were you in the nose week that appeared recently this year, of all the students that he's been promoted?
Oh, I didn't even know about that. Maybe.
I've got a copy. I'll look you up.
Okay, yes, oh man, I'm gonna look this up. My mother loves that kind of stuff. Favorite child, because I'm competing. I'm not even the best scientist in my family. My sister's just completed a MSc in chemistry and about to start a PhD, but she works on drugs, malaria, and malaria and TB drugs. So it's very hard to compete with that because she's saving lives. So if I can be Nose Week, I'll be golden. Any other questions?
Are you going to be dependent on saving the taxpayer for your living ad infinitum?
So the question is the taxpayer am I going to suckle at the teat of the taxpayer forever? That's how, well, unless they are privately funded fellowships, there are some privately funded fellowships, but most fellowships are funded by the government through taxpayer money. So the National Research Foundation and the SK is obviously funded by that kind of thing. And I don't know how the money works exactly, but if it's government money, it's taxpayer money. Yes?
Is the potential of fracking in the Karoo a big worry to the astronomers?
The question is about fracking and whether that's a danger to the SK project. Yes, and we're very nervous about it. We're keeping an eye on it. So far, the government is on our side because they've also put in a lot of resources into the SKA, so it would be silly for them to kind of undermine that, excuse the pun, at this point. But it is something that we are concerned about, and it is very it's very alarming when these requests keep coming up and then they get some backing up until a certain point, and so far that we managed to keep a lid on it. But I hope that someone sees sense and kind of just puts a moratorium on it completely, which I assume was the case until I think last year or so when it started coming up again.
I have one other little question, maybe this is a simple one. How do you change infrared or ultraviolet radiation, which is invisible to the human eye, into visible images?
Oh, that's a very good question. How do you image electromagnetic radiation that is invisible to us? So basically, you just kind of add false color. Like what you do is like a map, basically. In fact, they call radio images often radio maps. So when you're looking at a map and you're looking at a map of, say, the Cape Peninsula or so on, how do you know that the mountains are there? Because you're looking at them flat, right? So you draw contours. You draw contours, and then from the shape of that contour, you can build up what the shape of the mountain is, and it's almost exactly the same process.
What appears on the screen or on something?
It's basically just numbers. So all of these images, these are all false color images. They all come out as black and white, and then so it's a black background, and then like.
When it's all fives, then you make it green or something.
Yeah. Or if it's all twos, then yeah, and then you build up like a contour map like that. So yeah. So this, I guess, this is going to be the hottest. So that'll be all tens going out to like ones, and you build up the rings like that, and you put in the different colors.
Thank you.
Yes?
Can you talk a bit about big data? Because the whole thing of the
Yes.
mega computing.
Yes. So big data is a big buzzword, not just in the sciences, but also in industry. So that's also another thing that people in Blue Sky Science are very, very very well trained to be able to go into, and I know several people who have quit academia at various stages, halfway through a postdoc or halfway through a PhD even, or some people finishing just their MSc and going to work for data science firms and so on. In fact, I think UCT is, I think this year or next year, they're starting an MSc in data science. So basically big data is a collective kind of fuzzy term for being able to procure and manipulate and analyze huge data sets. So as you can imagine, the SKA being so physically big is going to also be it's the amount of data and it's going to be unprecedented. I don't have the numbers off the top of my head. I should probably put that in at some point next iteration, I'll put it in of this talk. But just how are we going to store that data? How are we going to process it so that end users like myself of this data, I'm not going to sit there and actually process every image. There's no way. I would need my own little cluster. So these big, they're building, for instance, the Center for High Performance Computing is very involved in that, and that is in Rosebank. And also they've launched the Inter-University Institute for Data Intensive Astronomy, IIDA. And it's very new. That's why the acronym's not rolling off the tongue, because they only signed it into being in November. And it's a joint effort between UCT, UWC, and the University of the Northwest to be able to, so they're trading up software engineers and they're getting all the infrastructure in place. And it's headed up by Professor Russell Taylor, who is a joint professor here at UCT and at UWC. So how to deal with these enormous, enormous volumes of data. And already, even before the SKA, I mean, the kind of data files that, not necessarily me, but that some of the people that I work with deal with and manipulate and extract useful information from is not the kind of stuff that you can just easily do on a desktop computer. And industry is very interested in people who are trained up in that regard, because every time you go online, like Facebook knows your whole life. Amazon knows your whole life. There's an apocryphal story about a man in the US who stormed into a Target, which is like a huge chain similar to Walmart. He stormed into the Target and demanded to speak to the manager and said, "Why are you sending my 17-year-old daughter pamphlets for baby bum cream and nappy rash and stuff like that? She's 17 years old. You shouldn't be marketing this stuff towards children." They're like, "So we're so sorry. It was obviously a mix-up." And then allegedly came back the next week and said, "Actually, my daughter is pregnant." And I found out when I confronted her about the coupons that you sent her. So they know all about, from your shopping patterns, how they know about your life. So, and that's a kind of the kind of useful information that you can extract from huge data sets, or just the frequency with which you do things, and so on. Like a lot of fraud is detected online. From irregular searching for irregular, funny patterns in your transaction history and so on, and that's the kind of stuff basically that you do in astronomy all the time. Whether the data is coming from a black hole in a galaxy, or whether the data is coming from someone's standard bank account, all you're doing is searching for patterns and trying to extract information. So that's definitely something that that is of interest, not just to astronomers, but in industry as well, and something that we are tackling head on. No, Rosebank here down the road. Yeah. Any other questions? I guess there's time for one last question. Yes?
Could you elaborate on your fracking scenario?
I don't, so this is again a question about the fracking. I don't know much about it, except that I get very panicky every time there's something in the paper about it saying, "Oh, we should be fracking in the Karoo because that's where the gas is." And then we get it pushed back or delayed, or they try to move it or something. Because, I mean, there's a lot of people, and you can understand where they're coming from. It's like, oh, building a telescope shouldn't be more important than having, having gas or whatever to heat houses and so on. But as I said, the government's put so many resources already into the SKA that fracking would basically undermine the entire thing, because you can imagine the kind of interference you would get with this very sensitive instrumentation. As I was talking about being able to track tectonic movements, you can imagine what a jackhammer is going to ruin the whole thing. So when I was visiting the Karoo site, for instance, you can't drive onto, like within kilometers of the site, you can't drive with a petrol engine, because the spark plugs of a petrol engine work such that they actually give off a small spark of radio, a burst of radio frequency interference or burst of radio light, and that can be detected. That would blow out the receiver on those telescopes. So you have to drive with a diesel engine always. So you can imagine the fracking will completely ruin everything. So that is, yeah, it's very stressful when those requests do come up. But I don't know at the moment. I mean, I'm not privy to that kind of thing. Maybe if you know Bernie, he'll tell you a bit more. But I know as much as people who read the newspaper know. Oh, so this is a question about the tectonic plate movements. No, you can just kind of track them, but it's not down to the level where I think that requires completely different kind of instrumentation, and that's more on a geology. I mean, there are no tectonic boundaries in Africa. Africa's pretty tectonic. Well, in this part of Africa, I mean, the Rift Valley is a different story. So you can track the movements, but I mean, we won't be able to help anyone in California by the San Andreas Fault. So, that requires different instrumentation.